Hello, welcome back to the first course in general physics. We are still discussing the subject of fluid mechanics. In the previous lecture, we have discussed fluids at rest after we have defined the essential parameters. And in this lecture, we will discuss two basic principles, important principles that are applied to fluids at rest. Pascal's principle and Archimedes' principle. We will talk about their applications. Later, after that, we will come to the discussion of the motion of fluids. But since the general motion of a fluid is very difficult to describe and to study, we will be limiting our discussion to the motion of fluids, of ideal fluids. We will define what are ideal fluids, and then we will derive the equation of continuity for the fluid motion, the ideal fluid motion, and then finally we will arrive at Bernoulli's equation from considerations of work and energy. As we have seen in the previous lecture, we derived the formula for the pressure at a depth h beneath the surface of a fluid. And we noticed that the pressure P2 at any point at depth h beneath the air-fluid interface is given by P1, which is the pressure at the interface, plus rho g h, where rho is the density of the fluid, g is the gravitational acceleration, and h is the depth of that point. As a consequence of this finding, Pascal's principle comes to play an important role in fluid mechanics. However, it was not until 1652 that Pascal stated this result in his famous principle, which reads, a change in the pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of the container. This principle, as we said, it's a consequence of the equation that we have derived, and it is obvious to notice that if we add a pressure delta P, if we exert an additional pressure delta P to the interface of the fluid, to the surface of the fluid at the interface between the fluid and the air and the atmosphere, then since rho and G and H of the fluid are not changed for an incompressible fluid, the density is constant for an incompressible fluid, we should remember. Since that is true, then a differential change, delta P, introduced to P1, an increase in P1 at the interface by delta P, will lead to an increase of delta B, a pressure change of delta P, exactly the same amount at point P2. And P2 is any point in the fluid, which implies that any change at the interface, at the surface of the fluid, will be transmitted. The same amount of increase in pressure will be transmitted to any point regardless where it is, because this change delta P in P2 as a resultant of the change in P1 by delta P will not be dependent on H, the location of the point, which leads to this a check of the correctness of this principle. This principle is of noticeable importance in application. One of the essential applications of Pascal's principle, is the hydraulic press. Sometimes we encounter a problem where we need to lift a heavy object, like an automobile, for example. We cannot lift that automobile using our own strength and our own force, our own human force. However, we can use Pascal's principle to construct a hydraulic machine, a hydraulic lever that will help in carrying out the job. And what does that machine look like? This is a simple diagram that illustrates the machine and its operation. It consists of some sort of a tube with a narrow end on one side and a wider end at the other side. The area of the piston covering the lower end, the narrower end, is A sub I. I goes for the input end, where we input the pressure, where we exert the pressure or the force, our force. And the area of the piston covering the cylinder at the other wider end is A sub O, going for output. O resembles or indicates output. This is where we need the output work to be accomplished, where we put the car to lift or the heavy object to lift. Now, this cylinder, these two cylinders are connected and filled with a fluid, an incompressible fluid. Incompressible fluid, we remember that the fluids are gases and liquids, but incompressible fluid is the type of fluids that are simply liquids. These are the incompressible fluids. To a good approximation, they are incompressible, like oil, for example. Now, in the narrower end, if we exert a pressure by introducing a force to the area A sub I at the input end of the lever, then the pressure that we exert on that piston is simply delta P is equal to the force that we exert, F sub I, divided by the area A sub I of that piston. Since this pressure change that is a consequence of our input force is transmitted to all parts of the fluid undiminished, as the principle states, then this very pressure, delta P, will be transmitted to the other end at the output piston. And the pressure will be exactly the same. That means the pressure of at the output piston, which is simply F sub O, which is the output force that the piston would exert on any load that is on top of it, divided by A sub O, that's the force divided by the area. And that is the at the output end. Since the two pressures are the same, we conclude that F sub I divided by A sub I is equal to F sub O divided by A sub O. And this gives us the result, a relation between the output force that we can gain, the relation of that output force to the input force that we exert on the narrower end of the lever. And that result is F sub O at the output end is equal to F sub I multiplied by the area A sub O divided by the area A sub I. That is the force we obtain at the wider end of the lever. If we look at this formula closely, we notice that since A sub O is larger than A sub I, then we conclude that if we apply a force F sub I to the narrower end, we get in return a larger force F sub O at the wider end of the lever. How much larger? This depends on our choice by choosing the relative ratio of the area A sub O divided by A sub I. The larger the ratio A sub O divided by A sub I, the larger is the force F sub O that we obtain at the wider end of the lever, and the heavier the object that we can lift. However, we must remember that there is a trade-off always. If we make the area A sub O infinitely large in order to get an infinitely large force, which is a dream, if we do that, since the fluid is incompressible, then as we press on the narrower end, we lower the piston at the lower end by a distance d sub I, let's call it, and that will lead to a change in the fluid volume at the lower end by delta V. It will be lowered and the volume pushed downward by our force is delta V. This delta V is the same as the delta V that the fluid is pushed in the other side, on the wider side of the lever. If the area is infinitely large at the wider side of the lever, then the displacement or the distance moved by the wider piston d sub O at the output side of the lever, d sub O will go to 0. D sub O will go to 0. That means we will not be able to move. Although the force is infinitely large, but the distance that we move the object is so small. So there is a trade-off between moving the object a significant distance, because that's what we are using the lever for. We use it to lift the objects a distance. So there's a trade-off between the amount of distance that we can lift the object and between the amount of force that we obtain by selecting the area A sub O with respect to the area A sub I. This machine or this lever will allow us to lift such heavy objects, which is something we appreciate, because we would like to lift heavy objects that we can't do it otherwise. But we have to remember that we move the narrower end where we input our force, we move it much larger of a distance d sub I with respect to the distance d sub O at the output, because delta V is the same in both sides. So we have to move the fluid a large distance. That means we pump many times, many strokes we pump at the narrower end where we apply our force in order to get some sort of an appreciable distance at the output end. One other conclusion regarding the incompressibility of the fluid is that if we work out the work done by us by pushing A sub I downward with our force F sub I, and the work we achieve by the fluid lifting the heavy object or the load at A sub O, situated at A sub O at that piston, by the force F sub O exerted by the fluid, the work we do, W sub I, is equal to the work achieved by the fluid, W sub O. And that is a consequence of the incompressibility of the fluid, since the work done is simply delta P times delta V. The work we do is delta P times the volume delta V of the fluid that we push down as we apply our pressure or our force F sub I. And at the end, at the other end, at the load end, the work achieved by the fluid or by the lever in lifting the object is W sub O, which is simply the pressure, which is exactly the same as delta P, as the input delta P, according to Pascal's principle, times delta V. And since the fluid is incompressible, delta V is also the same. So delta P times delta V is the same in both ends. The work is the same. So we don't achieve any benefit as far as mechanical work and energy is concerned. But what do we achieve? We achieve some other benefit. It's not in terms of energy. We cannot create energy from nothing. We cannot obtain more energy than we input, but we achieve the job of lifting an object that we cannot lift by our force F sub I. That is a great achievement for this application. The other principle that we are interested in talking about in the field of fluids at rest is Archimedes' principle. And this principle reads: a body fully or partially immersed in a fluid experiences an upward force, which is the buoyant force, that is equal to the weight of the fluid that the body displaces. This is the so-called Archimedes principle. This principle is talking about the buoyancy, the force that a fluid exerts on a body that is immersed fully or partially in it. The center of buoyancy, or the center of force, is situated at the center of the fluid that the object displaces, has it not been displaced. So the portion of the fluid displaced by the object, the center of mass of this or the geometrical center actually of that portion of the fluid that the body has displaced before its displacement, at that point lies the center of buoyancy, or the force that the fluid exerts on the object upward. And thus, if we immerse a uniformly dense object in a fluid, the uniformly dense object also has a center of mass which is at its geometrical center. The displaced fluid, has it not been displaced, has the center at its geometrical center, the center of mass or the center of buoyancy of the force, and also the object has the same point where the center of gravity is. So that means the two forces, which is the gravitational force applied to the object downward, which is its weight, is acting on the same line with the buoyant force, which is the weight of the displaced fluid, which acts upward. That means a uniformly dense object which is immersed fully in a fluid will feel lighter. Lighter by how much? Lighter by the amount of the weight of the fluid that it displaced. That is one of the effects of the buoyancy. what it does, it makes the objects immersed in the fluid feel lighter. We actually, even immersed in atmosphere, in the air that we are living in, we are actually a bit lighter than we really are, because we have displaced by our bodies a volume of the air, and we are lighter by the weight of that air of the atmosphere that we displace. But that weight of the air that is equal in volume to the volume of our bodies could be considered significantly small, up to the point that we can consider that the weight that we measure for ourselves is the true weight. But actually it's not, it's the apparent weight. So another effect of the buoyancy is that if an object is partially immersed in a fluid, and if it happens that the center of buoyancy is different than the center of gravity of the immersed portion of the object, then there are two forces not acting on the same line, which will introduce a torque on the object, and that torque will rotate the object until the two centers coincide, and then the two forces, the buoyancy force F sub b and the weight of the object, are acting on the same line, one upward and one downward. And that is why, for example, we see the logs, the wooden logs floating on the river. We see them floating, sitting flat with the surface of the water, rather than sitting with some angle with respect to the surface of the water. That's because of the torque applied to the object by the buoyancy force, and by the weight, of course. The two forces do contribute to the torque. And this principle of Archimedes has applications, and one of its nice applications is the evaluation or the determination of the density of objects, even objects which do not have a very simple shape that we can calculate their volume easily. Even such objects we can use Archimedes' principle to determine their density. That's one of the applications, and this application leads to the fact that we can, for example, the very old application of this principle that people were doing, we can determine if we are given, for example, a piece of gold. By Archimedes' principle, we can determine whether this piece is pure gold, or it is cheated, if it is alloyed with some other material, because gold has a given density which is very high, 19.6 grams per centimeter cube, I think, and if it is alloyed with copper, for example, which has a density much lower than that, of the order of 8 grams per centimeter cube, then the effect is recognized directly. And now, at this point, we would like to consider the motion of fluids, and we will be considering the motion of ideal fluids. And what are ideal fluids? Ideal fluids are characterized by several characteristics. One of these characteristics is that an ideal fluid is characterized by a steady flow. A steady flow, which we otherwise call laminar flow, is the flow of the fluid where the velocity of the fluid at any given point does not vary with time, does not change. This is a steady flow. The flow near the middle of a quiet stream is a smooth flow, and that flow can be approximated as a steady flow. The otherwise non-steady flow, if the fluid's velocity changes at a given point from time to time, we call that flow a non-steady flow or turbulent flow. The turbulent, this background of this slide shows the streamlines of steady flow, and the background of this slide shows a picture of the smoke of a cigarette, where in the beginning the flow starts as steady flow, and then after a while it becomes a turbulent flow, non-steady flow. The other characteristic of an ideal flow is that it is an incompressible flow. Incompressible flow in the sense that the density of the fluid is assumed to be constant, does not change with pressure or from point to point. The third characteristic of the ideal fluid flow is that it is a non-viscous flow. Effects of viscosity or viscous drag forces, which are dissipative forces like friction in the motion of solid objects, are ignored, or they are not present in this type of flow. Finally, the last feature of the steady flow is that it is an irrotational flow, which means that a body moving with the fluid does not rotate around an axis that goes through its center of mass. And we would like to define a parameter which is the streamlines that is characteristic of the ideal fluid flow. Streamlines are a given streamline is simply the path traced out by a fluid particle. If we follow the motion of a fluid particle, then the line that it takes, the trajectory that it takes, is a streamline. And the velocity of the fluid particle at any point is tangential to that streamline, tangential to the path it takes, which is natural consequence. And this figure shows streamlines of laminar flow or steady flow with a particle and its velocity which is tangential to the streamline, and the particle will be moving along that streamline. The motion accordingly of fluid will be like motion in a pipe, where a tube of flow is simply a hypothetical tube that has boundaries which are the streamlines. And this hypothetical tube, which is the tube of flow where the fluid flows inside, is really like a true pipe, because if a particle enters from one end, enters that tube, which is bounded by streamlines, then the particle cannot leave through the walls of this tube, because the particle doesn't change its velocity with time. Accordingly, the tube of flow works just like a real pipe, like a glass pipe or a metallic pipe. And this will lead us to what we call the equation of continuity, because if we consider a tube of flow, then at point B, we have the area between the streamlines is A sub 1, and the area at another point in the flow tube is A sub 2. Now, if a volume element of the fluid enters at B, this same volume element will leave the fluid at point C during a time interval of delta t, and that is a consequence of the incompressibility of the fluid. And that will lead us to the fact, since during delta t, delta V enters at A1 and it leaves at A2, that means that A1 times V1 is simply dx at A1 at the initial position by dt. So that will be A1 V1 equals A2 V2. Remember that A1 V1 is simply A1 delta x divided by delta t, which means delta V at the input side, and A2 V2 is simply A2 times delta x2 at the output side divided by delta t, and A2 times delta x2 is simply delta V2, but delta V2 and delta V1 are the same. So that gives us the equation of continuity, and this equation can be rewritten as the rate of change of the volume is constant. R is equal to A times V, because A1 V1 equals A2 V2 at any other point. So the general term A times V is a constant. This is the equation of continuity. This equation is not a new principle. It's not a new equation. It's just simply a reformulation or another expression of the conservation of mass. Whatever mass enters a tube, the same mass leaves, or whatever volume enters, the same volume leaves, assuming that the fluid is not compressible and also is characterized by a constant density. The equation tells us that the fluid is faster in the narrower parts of the tube. That is a consequence of the equation of continuity, since AV is equal to a constant. So the smaller the area of the tube, the faster is the fluid at those narrower areas of the tube, and that is also a consequence that we can see by in our everyday experience and life. And now we are at a point of considering Bernoulli's equation. Here in this figure, we see a tube having two different areas, and the tube has a general shape. If at the input side, at the lower end, if volume delta V enters with initial velocity V1, then after delta T, after this volume element delta V has entered into the tube, then the same element of volume delta V will leave the tube at the upper end at height y2. So in that sense, we have work that is done on the element of fluid delta V, and that work is simply the input work to the system. Our system here is the fluid in blue in the tube. As we push the fluid element delta V into the tube, P1 exerts work, which is W1, we can call it, and this work is simply P1 times delta V. The fluid at the higher end at Y2, when it pushes the same amount of fluid delta V outside this tube, it exerts work on the surrounding, on the environment, which is equal to P2 times delta V. Also, delta V is the same. So the net energy introduced in terms of work into the system is simply P1 delta V minus P2 delta V, because at P2 the fluid at Y2 the fluid does work on the surroundings. Also, there is, as the fluid element delta V as it rises, the gravitational force introduces work that is negative on the on this element of fluid, and also we have the kinetic energy in the initial end is 1/2 times delta M times V1 square, and delta M is simply rho times delta V, and at the higher end at Y2 the volume element has a kinetic energy 1/2 delta M, which is the same as delta M, the initial delta M, times V2 square. So calculating the work done and using the work energy theorem, we arrive at this equation: P1 plus 1/2 rho V1 square plus rho GY1 equals P2 plus 1/2 rho V2 square plus rho GY2, or P plus 1/2 rho V square plus rho GY is equal to a constant. And as consequences of this equation, for fluids at rest, we eliminate V. V is 0, and we obtain the same equation that we obtained previously for fluids at rest. P2 equals P1 plus rho G into delta Y. And finally, for a horizontal tube, if we assume y1 equals y2 is equal to 0, we obtain P2 equals P1 plus 1/2 rho into V1 square minus V2 square. At this point, I end the lecture and thank you for your attention.